Okay, in this problem we're looking at a block of mass m that we can convert to a weight. All right, so I'm showing that with the symbol W, and it's sitting on an inclined plane, and there's it's not a smooth surface, so there's some friction component that's keeping it from sliding down the plane. Okay, so what we have here is an angle theta, and what I want to do is take a look at what is the angle theta to where this block will start to move. All right, so let me write that down. At what angle theta does the block start to slide? Okay, and what we're going to assume here is that there's a coefficient of friction mu s, all right? And so that's one thing we're given. All right, so let's get started with that. So what I've started with here is a free body diagram, and I'm taking a little different approach where I'm drawing the coordinate system slightly differently. And I thought of this because a student actually asked me a question. They said in physics, when we do inclined plane problems, we put the coordinate system along the plane, and asked if that was okay. And sure it is. You can use a different coordinate system, and there are some advantages to using this one. The two advantages are that you have this force Fs that's moving strictly in the x direction, so you don't need to resolve that force any further. And you have the normal force N that's moving in the y direction. And so both those components are already resolved for you along this coordinate system. So that just leaves you with the weight force that you need to break into components so that we can do this sum of forces equations to look at the equilibrium point for this problem. Okay, so here's the trick. All right, I'm going to change this to purple. It's really a lot easier to solve if you know this angle is theta. Okay, and so think about that on your own. Try to figure out why that is the case. For me, the way to see it, I'm going to draw this in a different color. All right, if I draw a line in the x direction with this coordinate system, okay, and then I draw something horizontal, all right, to me, I know that this angle is theta. All right, and I also know that this forms a 90-degree angle because that's the definition of perpendicular. All right, so that means this one, theta, 90 minus theta, is this angle. All right, and then finally what I know, I'm going to change the color again, is that this angle is 90 degrees, which logically implies this must be theta. All right, so think through your geometry, but that's how that works if you're confused on how I just move that angle theta around. Okay, you work a few of these problems and you start to see it pretty quickly. All right, so I'm going to erase all those extraneous marks, clean this up a little bit, and basically we are resolving W into the coordinate directions. All right, so let's get started. Sum of forces in the x direction, where this is the x direction shown by this coordinate system. All right, so what I have here is I have Fs working to the right. Okay, so I can put things that are working to the right equal to the things that are working to the left. All right, and so working to the left would be the weight vector resolved into this direction. Okay, I did that wrong. It's not that direction, it's perpendicular, right? It's this direction. All right, that's good because we needed this to be a right triangle. Okay, so I look at that, and that's the opposite of theta. So that would be W sine theta is Fs. Okay. All right, so that's one equation. The other thing we have is that sum of forces in the y direction have to be 0. And what I have in the y direction is the normal force working up. So I put everything up, working up on one side, everything working down on the other. On the other side of the equation, I have what's working down. And working down is this component. I'll draw this in red. This component coming down, which would be cosine of theta, because it's adjacent to that theta angle. All right, so that would be W cosine theta. All right, so we have those two equations. Now normally what happens is, for a given theta, Fs will adjust to be equal to W sine theta. Okay, and the normal force is just by what's given here. All right, but if we start to tilt the plane, increase theta, all right, then there's only so much that the friction force can apply, and once that's exhausted, is one way of thinking of it. Once you exceed what that would be, the block starts to slide. Okay, and so what we know about friction forces is that the maximum friction force that can be exerted is mu times the normal force, okay, or mu s. All right, so we assume that we knew mu s in this problem, okay, and so what that means then is I can take this quantity, Fs equal mu n, and I can plug it in to the equation here. All right, I also know what n is, and I can plug that in. All right, so let's do all that. All right, so what I have is mu s times n, but n is W cosine theta. All right, so that part is n. Okay, so that's just the maximum friction equation that's right here. All right, so equal to W sine theta. All right, so I'm actually right where I need to be, okay? I can now solve for mu s. Mu s is sine of theta over cosine theta, which is tangent theta. All right, so if I wanted to solve for theta, I would do the arctangent, all right, and that would give me the maximum theta I could have before the block starts to move. All right, so this is actually a well-known result, and if you think about it, this would be an experimental way to measure the coefficient of friction between two surfaces, the coefficient of static friction. Okay, so what you could do is you put a block on an inclined plane, adjust that angle. As soon as the block starts to slide, you record that angle theta, take the tangent, and you get the coefficient of friction. All right, so we're going to do that in an exercise this week, so I wanted you to know about this topic.